Dear friends, today we will discuss an important property of open set. Every open set in complex plane can be written as a countable union of compact sets. So now we state the proposition. If G is a open set in the complex plane C, then there exists a sequence of compact sets Kn such that G can be written as union of Kn where n runs from 1 to infinity. Moreover, the sets Kn can be chosen such a way that Kn is subset of interior of K of n plus 1, and if K is a compact subset of G, then there is a natural number n naught such that that compact set K is a subset of K naught. Proof of this proposition. If G is an empty set, then there is nothing to prove. So without loss of generality, we can assume that G is non-empty. So given that G is an open subset of complex plane C, maybe G is bounded, maybe G is unbounded. Okay. One comment: since G is non-empty, so if we take some complex number from G, then obviously there exists a natural number in such that n is bigger than modulus of that complex number. So, because the set of natural numbers is unbounded. Okay. So the construction of the compact sets lies in this observation. Okay. First we consider a disk. Consider those complex numbers whose modulus is less or equal to n, where n is a natural number. So this is the closed disk of radius n. Okay. A closed disk of radius a. Okay. Now we are considering those complex number whose distance from the complement of G is greater or equal to 1 by n. So we are considering this set. Okay. So here we just recall one definition, that distance of a point from a set is nothing but the infimum of distance of x comma y, where y belongs to the set A. Okay. So here we are considering those complex number whose distance from the complement of the set G is greater or equal to 1 by n. Okay. So this is the set complement of G. Okay. Now we are considering those complex number whose distance is greater or equal to 1 by n. So obviously those complex numbers do not lie outside of the set G, because if we take any point from the outside of the set G, then the distance from those point to the complement of G is 0. So obviously those point lies inside G, and obviously those points do not lie on the boundary of G, because if we take some points from boundary of G, then distance of that point from complement of G is 0. So obviously those points entirely lies inside G. Okay. So this is the set of all those complex numbers whose distance from complement of G is bigger than 1 by n. So this is the set, and this is the closed disk. Okay. So this is the set, and this is the closed disk. Okay. Okay. So now if we consider the intersection of these two sets, then the intersection region is this region. Okay. And this intersection we call as the set Kn. Okay. First observation, that this set is a bounded set. Okay. And since Kn is subset of this set, so obviously Kn is bounded. Okay. Again, you see that this set is a closed set. Okay. And obviously this set is also closed set. Okay. So intersection of two closed set is closed. So obviously Kn is closed. So Kn is closed and bounded. Okay. Since we are considering Kn in C, that is actually R2. So by Heine-Borel theorem, Kn is compact. The second observation is the set of all complex number whose modulus is less or equal to 1 by n. This set is a proper subset of set of all complex number whose modulus is strictly less than n plus 1. And the set of all complex number whose modulus is greater or equal to 1 by n is proper subset of collection of all complex numbers whose modulus is strictly greater than 1 by n plus 1. So this is obvious case. Kn is a subset of interior of k of n plus 1. Okay. Now you see that each Kn is a subset of G, that is union of Kn n equal to 1 to infinity is a subset of G. Okay. Now if we choose complex number from G, then there exists a n belongs to n set of natural numbers such that modulus of Z is less or equal to n, because the set of natural numbers is unbounded. So this observation help us to construct a knot such that Z belongs to some Kn, and that K naught is a subset of union of Kn equal to 1 to infinity. So obviously from figure it is clear that G can be written as, by construction we can conclude that G can be written as union of Kn or n runs from 1 to infinity. Okay. Okay. So we have seen that G can be written as union of compact sets, countable union of compact sets, and each compact set is a subset of interior of Kn plus 1. Each Kn is subset of interior of Kn plus 1. Now observe that interior of Kn plus 1 is open set. Okay. Now if K is a compact subset of G, then K is a subset of G and G is nothing but union of Kn n equal to 1 to infinity, and by this property we can write that G is nothing but interior of Kn n equal to 1 to infinity. So interior of Kn is an open cover of K. Okay, since K is compact, so this open cover has a finite subcover. There exists n1, n2, nk such that K is a subset of interior of Kn1 union interior of Kn2 union interior of Knk, right? So K is subset of Kn1 union Kn2 union Knk. Okay. So if we take the maximum of n1 into nk and say the maximum is m, then K is subset of Kn. So if K is a compact subset of G, then there exists a natural number m such that K is a subset of that compact set. Okay, and this completes the proof. So the main theme of this result is that every open set in a complex plane can be written as countable union of compact sets. Okay, and this result is also true in Rn also. Every open set in Rn can be written as countable union of compact sets. Okay, thank you.